So far, we've done two types of vector operations. We've done vector addition and also in the process subtraction. And we've also done we've multiplied vectors by scalars to either flip the direction of the vector or make the vector's magnitude longer or shorter. Now we're going to study something called a dot product, which is when we multiply one vector by another vector. And this concept is a little bit tougher to grasp sometimes just because it doesn't have a direct graphical representation. Like when we do vector addition, we can directly see the resultant vector. Whereas with dot products, when we multiply one vector by another vector, we actually get a scalar. We don't get a new resultant vector. It produces a scalar. And what we actually are going to use this scalar for is when we actually want to find the angle between two vectors. And we'll do that in a little bit, but I just want to make sure that we understand that a dot product results in a scalar. The way we actually find a dot product is that we go ahead and we multiply together the horizontal components. So we're going to multiply u1 and v1 here in this case. And then we're going to multiply the vertical components, or u2 and v2. And we are then going to add up those products. So you multiply the horizontal, multiply the vertical components, and then add up those two products. And that is what we call the dot product. Your textbook provides a couple of different properties for the dot product, and I don't want to go through too many of them right now in depth because I think they're mostly intuitive if you follow the order of operations. One that I do want to highlight, or a few that I want to highlight for you, if we look at the third property here, just making sure that we understand that this is similar to like the distributive property. When you add up vector v and vector w, you get a resultant vector. And so doing the dot product of u and some resultant vector v plus w is equivalent to doing the dot products of u and v, the dot product of u and w, and adding those two dot products up. Number 4, we see that the dot product of any vector and itself is actually the magnitude squared. And the reason for that is if you think about this, if you take v sub x comma v sub y, and you multiply it by itself. So again, v sub x, v sub y. Then what you end up with is v sub x, this squared, plus v sub y squared. And what we're saying here is that this is equal to the magnitude of vector v squared, right? Because we would see that taking the square root of this is equal to the square root of that. And what is that just simply? That is just the magnitude of vector v. And that's equal to what we see there, which is a standard formula to find the magnitude using the distance formula. Finally, for number 5, that property just simply says if you find the dot product of two vectors and multiply that dot product by some scalar c, that's equivalent to doing c times some vector u and finding the dot product of that with some other vector v. Again, this is kind of, you can think about this a little bit like the associative property. Don't worry too much about these properties. Again, I think a lot of them come up pretty organically and intuitively as you work through them. But let's just do a couple of quick examples of finding dot products. Looking at A, if I ask you to find the dot product of these two vectors, it's about as easy as it gets at this level. We would just simply find 4 times, oh, I actually don't need those braces. We would say 4 times -2. So we're going to multiply together our horizontal products. And then we would go ahead and add that to 5 times 3, our vertical components. And that would just give us -8 plus 15. Our dot product is 7. Again, we don't get a new vector from this, we get a scalar. If I ask you to do this for B, which I will let you pause and try on your own, but remember, vector u is just simply written as a linear combination right now. It's written in standard form. If you wrote this in component form, you would simply have the following vectors. And you can just apply the dot product there. And you can check your solutions with what I have uploaded in Google Classroom. Let me jump to something like A here, using properties. So we're given 3 different vectors here, and we're going to find the dot product of u and v. So again, we don't actually have to use the properties. We can just kind of do this bit by bit. First, the dot product of u and v. I would say, all right, the dot product of u and v is -1 times 2, again, our horizontal components, plus our vertical components, 3 times -4. And remember, that dot product is going to give us a scalar, which we'll multiply in a moment. And then we're going to take that and we're going to multiply it by, and I'll just do this in a different color, times vector w, which is 1, -2. Well, what do we get when we do the dot product of u and v? That gives us -2 plus -12, which is -14. Then we're going to multiply that by 1, -2. And again, this just simply gives us a new vector now, -14, +28. All right, I'll let you try B on your own, and again, check your solutions with what we have in classroom. Let's now try a problem where we're going to use the dot product to find the magnitude of this vector u. So again, this vector u is written in standard form right now. If I were to write this in component form, I would write it as the following. And so we already know how to find the magnitude of a vector. But what we want to do is we want to use the dot product to find the magnitude of this vector. And this is essentially us leveraging this property back up here, number 4. So what we're going to do is we're going to multiply this vector by itself. So we're going to say, let's multiply 6, -10 by 6, -10, this vector, multiplying it by itself. Well, what does that give me when I do the dot product? I get 36 plus 100, which is 136. And our property tells us that this here is simply our magnitude squared. So to figure out my magnitude, I'm just going to take the square root of both sides. The magnitude of vector v is equal to root 136. Those are equivalent. So far we've done this work to find dot products, but we haven't really discussed yet what these dot products do. What are their purpose? Well, one of the purposes of finding a dot product is because we use the dot product to find the angle between vectors. So far, we've already looked at finding the direction angle of a vector, but what we can also do is take two vectors that have the same initial point and find the angle between them. And I should probably specify here that technically there are two angles between vectors. There's the theta that's listed here, and there's also this angle here. So to be a little bit more specific, what we're actually finding is the smaller angle between the two vectors, what's indicated here as theta. So if theta is the angle between these two non-zero vectors, then we can say the following, that the cosine of theta is equal to the dot product divided by the product of our magnitudes. The cosine of theta is equal to the dot product divided by the product of our magnitudes. Another way to write this is also to say that the dot product is equal to cosine of theta times the product of our magnitudes. And that's just simply multiplying both sides by the denominator. So let's jump into an example of this. So for number 1 here, we're going to find the angle between these two vectors. So we say cosine of theta is equal to the dot product of u and v divided by the product of their magnitudes. The product of u, magnitude of u, and the magnitude of v. Well, let's find our dot product. The dot product is going to be 2 times 3, so 2 times 3 are horizontal components, plus -4 times +6. And we're going to divide this by the magnitude of u and the magnitude of v. I don't need to show any separate work. We know the magnitude of u is simply the square root of 2 squared plus -4 squared. So 2 squared plus -4 squared. And we're going to multiply this by the magnitude of vector v, 3 squared plus 6 squared. So clean this up just a little bit. 6 minus 24, that's going to give us -18. And then this is going to be root 20 or radical 20 times radical 45, which should be root 900. So we say that the cosine of theta is equal to this. So using inverse trig functions, we can say, all right, then that means theta is equal to the arc cosine of 18 over root 900, which is, I should say approximately, because it's an approximation, approximately 126.87 degrees. Okay. So try number 2 on your own. Pause the video and try number 2 and see if you're comfortable with the process of finding the angle between two vectors. Now, I want to close this video by actually going over one of the applications for the angles between vectors, or understanding the angles between vectors. And that's discussing something called orthogonal vectors. Orthogonal simply means that vectors are perpendicular to one another. So we would say that u and v, our two vectors u and v, are orthogonal to one another if the angle between them is 90 degrees. Another way of saying this is if their dot product is equal to 0. Now, pause and think about why that is the case. Why does this mean the same thing as saying that u and v are orthogonal if the angle between them is 90 degrees? Well, the answer, if you've had a chance to kind of stew on that, is that if the angle between the two vectors u and v is 90 degrees, we would say that the cosine of 90 degrees is equal to u dot v over the magnitude of u times the magnitude of v. Well, what is the cosine of 90 degrees? It's 0. So what we're saying here is even if we multiply both sides by 0, if the angle between two vectors is 90 degrees, or that their two vectors are perpendicular to one another, that means their dot product has to be equal to 0. So that's one of the applications of finding the dot product, is if we see that the dot product is equal to 0, that means the angle between them is equal to 90 degrees. Well, what about parallel vectors? Can vectors be parallel? Parallel, I don't know why I said it that way. Can vectors be parallel? Absolutely. Well, what does it mean if vectors are parallel? Well, it means simply that one vector is a scalar multiplication of the other. We would say that u, let's say u is equal to, let's say u sub x, u sub y, and just so we have something to reference. And vector v is v sub x comma v sub y. Well, there are a couple of ways of thinking about this. If one vector is simply a scalar multiplication of the other, so example, let's say vector u here is equal to 1, 2, and vector v is equal to, let's say, 3, 6. We could say that vector v is equal to 3 times vector u, or 3u. That's the same thing as the following here. We see clearly that vector v is simply vector u multiplied by a scalar of 3. What's another way of expressing that, or determining whether or not two vectors are parallel? Well, we can see effectively, what do we know about two lines that are parallel? We know that means they have the same slope. So we can say that the slope, or m, of u, in this case, is 2 over 1, which is 2. The slope of vector v is 6 over 3, and that's also equal to 2. Therefore, we say u and v are parallel to one another. So those are two different ways that we can express or justify two vectors being parallel. We can look at their slopes, or we can show that one vector is simply a scalar multiplication of the other. So I just want to show one of these problems, and I'll let you have a chance to try a few of these on your own. So are these vectors orthogonal, parallel, or neither? So let's just start by looking at their dot product, u dot v. Well, that's going to be 2 times 6 plus negative 3 times 4. Well, we see here that that is going to be 12 minus 12. That's equal to 0. Therefore, u and v are orthogonal. Okay? And let me try jumping to something like number 3. I'll let you try number 2 on your own, but let's jump to something like number 3. Number 3 says the following. Are these vectors orthogonal, parallel, or neither? Well, I could say, since one option is to look at the dot product, but I want to kind of hold on that for a bit, because earlier I said if two vectors are parallel to one another, that means their slopes are equivalent. Similarly, if two vectors are orthogonal, that means that they're perpendicular, meaning their slopes should be opposite reciprocals of one another. So u here would actually be written as 3/4 I minus 1/4 j. That's in standard form. U in component form would be 3/4 negative 1/4. And vector v in component form would be 5, 6. So if I look at the slope of u, that would simply be negative 1/4 divided by 3/4, or times its reciprocal, times 4 over 3. I should probably make that negative. Sorry for the dog barking in the background. I don't know if that's picking up. Neighbor's dog is mad about something. All right, so that's equal to negative 1/3. Now, if we look at the slope of vector v, that's going to be equal to, rise over run, 6 over 5. Now look at these two slopes. What we would then write is the following. We would say U and V are neither orthogonal or parallel because the slopes are not equal or opposite reciprocals. So there's my full justification here to indicate how we know these vectors are neither orthogonal nor parallel to one another. So again, try numbers 2 and 4 on your own and go ahead and check those in classroom, and hopefully by the end of it, you're pretty comfortable finding dot products and using those dot products to find angles and whether or not vectors might be orthogonal, parallel, or neither.